Let's take a look at kinematics and velocity. What is kinematics? Kinematics is a branch of mechanics that is concerned with the motion of objects without reference to the forces that cause the motion. So basically, kinematics is the study of motion without talking about forces. Whereas dynamics, our next section, will be the study of motion that involves the forces. The same equations are going to govern the motion of all objects, whether they're on Earth or in space.
Everything in the universe follows the laws of physics. We have to make approximations and calculations since there are many variables that can affect motion. There's wind resistance from air and friction from the ground. The acceleration due to gravity also varies between celestial bodies. But objects near the Earth's surface accelerate downward with a rate of 9.8 meters per second squared, which is the value that we'll be using in this course for free fall acceleration. On the moon, however, it's going to be 1.6 meters per second squared because of its smaller mass. So we have a few equations to look at for kinematics.
The first one here tells you the final velocity of the object if it starts with some velocity and has an acceleration for some time. So this is for velocity after an object accelerates or increases in velocity. So obviously you have to take the initial velocity plus account for any acceleration to get its final velocity. The next equation is called the position function. Position function, because it is the final position or displacement of the object as a function of its initial displacement plus any constant velocity times a period of time plus any acceleration times a period of time. If the object is not accelerating and this factor is 0, then the equation becomes shorter and you can find final displacement after an object has traveled a constant velocity for some time. Okay, the third equation tells you the final velocity of an object if you know its acceleration and the displacement it covered during that acceleration. This is for average velocity. Average obviously means you add things together and divide by the quantity that you have. So this is average velocity times time will give you displacement of an object over that time. And lastly, the line over the V indicates average or constant. And that is, again, where you take the final velocity and the initial velocity and divide by those two, or divide by 2. So this is what you see right here. Okay, so if you want to know what the average velocity is, just take the final initial velocity and divide by 2. Okay, let's get started with velocity. In this section, you're going to differentiate between speed and velocity, calculate velocity, understand that velocity involves displacement and requires a coordinate system. So velocity is speed with the direction. It's represented by a vector, an arrow. For example, 4.5 meters per second is a speed, and 4.5 meters per second towards the highway is a velocity. Again, to calculate average velocity, you take the displacement divided by the time. So df is for the final displacement of the object, subtract di, the initial displacement of the object, and divide by the time interval over which that change in position occurred. The average velocity tells us the average velocity that an object was in motion over a certain time period. Now, this can also be the constant velocity if the velocity does not change. So average is the same as constant in some cases. Velocity can have a positive or a negative value. If particle A has a value of 5 meters per second and particle B has a value of negative 5 meters per second, that means they're moving in opposite directions. So this is A, and it has a velocity of 5 meters per second, positive, and particle B could be moving in this direction, so its velocity would be negative 5 meters per second. Let's do some examples. In your science notebook, go ahead and label this class examples velocity. This is 1A. So Jason sprints 50 meters in 6 seconds, stops, and then walks back to the starting line in 40 seconds. Sketch a coordinate system. So I don't need to draw a full y-axis because Jason is moving horizontally. So this is my x-axis. This is the origin, or 0 meters. And over here I have a point marking 50 meters. So he sprints 50 meters in 6 seconds, and then he stops. So here he goes 50 meters over the course of 6 seconds. And then he stops and he walks back to the starting line in 40 seconds. What is the average sprint velocity? Well, the average velocity is going to be his final displacement, which was 50 meters. By the way, I'm going to call this direction the positive direction, and on the left side of the y-axis will be the negative direction. So on average, he goes a final displacement of 50 meters minus initial displacement, which was the 0 mark, divided by 6 seconds. So final time was 6, initial time was 0 when he started the stopwatch. Use parentheses around the numerator and denominator when you're plugging this into your calculator. So basically 50.0 meters divided by 6.00 seconds gives us 8.33 meters per second. Bubble in your answers or highlight them. For B, what is the average walking velocity? Average velocity equals final displacement, which was here. So final displacement was 0 meters minus the initial position. He started at 50 meters when he started walking, divided by the final time would be 40 seconds, minus the initial time, 0 seconds. So in this case, for walking, we have a value of negative 50 meters over 40 seconds. And that's going to give us negative 1.25 meters per second. So the negative indicates the direction, so we don't have to say like 1.25 meters per second back to the origin. We can just say negative 1.25 meters per second because our coordinate system was drawn and the diagram indicates what direction negative and positive is. For C, what is the average velocity for the round trip? The average velocity is going to equal his final displacement, which was at the 0 mark, minus the initial position, which was at the 0 mark. So you can see here already that even though it took 46 seconds, the answer is still going to be 0 meters per second. It's kind of mind-boggling because you would think, okay, what is the average speed? But we're not talking about speed here, we're talking about average velocity. So if you go over the whole trip is 0 meters per second. This will make more sense when we talk about graphs. You can kind of get a visual of what's going on. Here's a y-axis and an x-axis. Here is the displacement, and here is the time. Now, Jason started at 0.0, and in 6 seconds, we'll call this 5, 10, 15, 20, 25, 30, 35, 40 seconds. In 6 seconds, he goes 50 meters. So he has a high velocity. Then he stops and he walks back to the starting line in 40 seconds. So that puts him at 46 seconds over here. Now, granted, he's going at a constant velocity and he ends up back at his starting position at 0 meters. You can see that because his final position was the same as his initial position, his average velocity for the entire trip is 0, flat line. On D, what is the average speed for the round trip? Well, speed is total distance over total time, and his total distance covered was 100 meters. And the total time it took him to cover that 100 meters was 46 seconds, making his average speed for the whole trip 2.17 meters per second. If Jason's average walking velocity were changed to negative 1.50 meters per second, then how long would it take him to return to the start line? So previously, his walking velocity was negative 1.25 meters per second. Did his speed increase or decrease? It says it was changed, but did it increase or decrease? It was 1.25, and now it's 1.5, so his speed increased. Don't let the negative confuse you, that says direction. So would that mean it would take him a longer amount of time or shorter amount of time to cover that 50 meters? If he was going slower before and it took him 40 seconds, it should take him a smaller amount of time since he's going faster. So his average velocity was changed. Velocity is a change in position over a change in time. Page break. His velocity is now negative 1.50 meters per second equals his change in position. His final position is 0 meters. His initial position was at 50 meters for the walk. Divided by the amount of time, we want to know how long it would take him now. Multiply by t on both sides. And then divide by negative 1.50 on both sides. So negative 50 divided by negative 1.50 gives us 33.3 seconds. So it took him a shorter amount of time because he was going faster. Number 2, if a person travels around the world in 80 days, A, what is the person's average speed during this adventure? It says speed is distance over time. The total distance covered would be the circumference of the Earth, 40,075 kilometers, divided by the time, which was 80 days, equals. Now, if y'all want to try these on your own first, pause this video and then come back. Pause it now. Welcome back. Did you get 500.94 kilometers per day? We have to convert that to SI units, so we need to convert it to meters per second. So one day is equivalent to 24 hours. I'm going to convert my time first. And then an hour is equivalent to 3,600 seconds. Now I'll convert kilometers to meters and crunch those numbers. What do you get? You should get 5.7979 meters per second. What is the average velocity for the trip? Well, did you learn from Jason's experience where he returned back to where he started from? Same concept. If you go around the Earth, all the way around and back to the same position that you start from, the average velocity for the entire trip is 0 meters per second.